Hello class, welcome to this video on AP Statistics, Chapter 3 review. So we're looking at, we're at part 3, we're in lesson 3 now. So we're in the home stretch here. We don't have too many more questions. We got about 12 questions left on this. So transforming nonlinear data, transformations here. So number 39, for the relationships between each pair of variables below, determine which model would be the most appropriate. Linear, exponential, or power. So explanatory, we got the length of the wall, and the response variable is gallons of paint needed to paint the wall. Okay, now we want to keep in mind that the gallons of paint, if X is the length of the wall, so let's say this is the wall, and X is the length of the wall, well then let's say that let's just assume that we have a square wall. Then if we have a square wall, then it's an X by X wall, right? Dimension wall. But if it's not, if it's a rectangular wall, let's just assume that it's shorter than it's longer, right? It's not as tall as it is long. Well, then either way, it's going to be like X minus 10 or whatever it is, right? Or it could be like half as tall as it is long. Whatever the case may be, because we're painting the wall, we're painting it in 2 dimensions, right? And so we would expect that the amount of paint we needed varies with some kind of squared power of X, right? It's not just based off of the length, but it's also based off of the height, 2 dimensions. And so whatever the case may be, let's just say we have 0.5X and X. Well, then the amount of paint Y is going to be based off of the area of that wall, right? 0.5X times X. The area times, some kind of times the price, or not the price, the paint. How much area can the paint cover? So let's say the paint can cover a certain area per amount or something like that. So either way, we would expect that we would need something that has a power function, right? X to the second power or something like that. We would expect that would be the case based off of the surface area of the wall. And so I would say that this one necessitates a power function. So I'm going to say power function for this one. Explanatory for the part B, explanatory, we got a year, response, amount of money in a savings account earning compound interest with no withdrawals made. Well, if you're doing compound interest, well, the formula for compound interest is P times 1 plus R over N raised to the NT power. Compound interest accrues the more and more. So the more interest you have, the greater the amount you get, or the greater your principal, the greater amount of interest you have, and the more interest, and then as time proceeds, you actually gain more and more interest, right, over time. And you gain it exponentially. So this is an exponential, no doubt about it. And if you have a continuous compound interest, then it would be PE, the principal, times E raised to the RT power, where R is the rate, the percentage, the rate of the growth, and then T is the time. So in any case, it's going to be exponential. So number 2 is going to be exponential. And part C, explanatory, the number of people at a party. Response is the number of pizzas ordered for the party. So we would expect that the greater the number of people, the greater the number of pizzas. And we would expect that to be a linear. I wouldn't expect that to be a quadratic or anything like that. So I would expect that to be linear. So if for every 2 people that arrive, you need to order pizza, I would expect that to be the same, right? I wouldn't expect that to really change very much. Okay, so number 40. The scatter plot shows the number of annual scholarly publications on the topic of AI, where X is the number of years since 2010 and Y is the number of publications. And this looks to be curved, right? In fact, it looks to be like it goes like this and then levels out. That's interesting. So describe the relationship between the years and the number of publications. So it appears to slowly increase and then quickly increase, right, after a certain point. So the number of publications increases slowly, then more rapidly over time. It appears to follow an exponential pattern. All right, so or part B, a linear regression model for this data is calculated. The residual plot is shown. Is the linear model a good fit? Well, we could see there's a leftover pattern here, so it can't be a good fit, right? So a linear model would not be a good fit. So no, it would not be appropriate due to the leftover pattern in the residual plot. Okay. All right, so part C, it is suspected that the data follows more of an exponential pattern. That's what we were mentioning earlier. Suppose we transform data so that the response variable is the log of the annual number of publications. Predict what you think the scatter plot will look like. Well, if we took the log of the publications, the publications is y, right? So if we took the log of y, so we took this and did log of y versus x, well, I would expect that it would be linear or close to it. The reason being is that if this is supposed to be a exponential, then it would follow the template y equals ab to the x power, right? If I take the log of both sides, I would get log of y equals log of ab to the x. I'm going to bring down the x power. Well, actually, first I'm going to split this up into a log of a plus log of b to the x. Now the x, I can bring it down as a power, so that's what I'm going to do. So I'm going to bring it down as a power, or as a coefficient, right? And so notice that if I graph log of y versus x, I get a line. This is a line of the form a plus bx, if you can see that, or mx plus b, same thing. And so I would expect that to be linear, right, based off of that. So predict what you think the scatter plot will look like. We would say the data will appear linear, and we don't have to necessarily explain that, because if you looked at your notes, you would say if I graph log y versus x for an exponential, then it should appear linear. If I have something that's a power function, then I would have to graph log of y versus log of x for it to appear linear. All right, so now for part D, it says the equation for the new regression line for the transformed data is given. So log of y equals that. Use this model to predict the annual number of scholarly publications on the topic of AI in 2019 to the nearest publication. Remember, this is the year since 2019 or 2010, so that means x is 29. X is 19, or 9. I'm sorry, 9. 9 years since 2010. All right, so log of y is equal to 5.2096 plus 0.0402 times 9. So we're going to do that calculation. Times 9. So you get 5.5714. All right. So now that we got that, so we get log of y hat equals 5.5714. Now to solve for y hat, right, we have to, the base of log is 10, so we got to do 10 raised to both sides. Okay, so y hat equals 10 raised to the 5.5714 power. Okay, so we get 372,735, I guess we can round it, publications. Okay, all right, so it takes care of that one. So number 41, the population of Austin, Texas has been growing exponentially since 1950. The scatter plot graphs years since 1950 versus the log of the population of Austin, Texas. Okay, so this is log of y, and this is just x. The equation for the least squares regression line is shown. X is the year since 1950, y is the log of the population. All right. So interpret the meaning of 5.0941 in the least squares regression line equation. Okay, so they're talking about this right here. Okay, all right, so interpret the meaning of 5.0941 in the least squares regression line equation. So in this case, this means that when x is 0, you would get 5.0941, right? So the population. So the predicted population of Austin, Texas is, so in 1950, because x is 0, so that means it's the year 1950, is 5.0941. Now this is going to be technically is 10 to the 5.0941, right? Because it's a log, but if we're just taking the y, we could just put 5.0941. It's not a big deal, but technically speaking, it's 10 to the 5.0941, 10 to the 5th power. That's the population. Interpret the meaning of 0.0172. So I guess I should say the predicted log of the population. I guess I could say that. The log of the population is 5.0941, which means that the actual population is going to be predicted to be 10 to the 5.0941 power. So we'll just include that. Interpret the meaning of 0.0172. Well, that's a slope, right? So it's 0.0172 people per year, right? Per invisible one there. So for every year, additional year after 1950, the population, for every additional year since 1950, the population, the log of the population is going to increase by that much. Okay, so basically, so we'll just say that the log of Austin's population is predicted to increase by 0.0172 for each additional year. All right, or per year, you could say per year. All right, so for part C, use this least squares regression line to predict the population of Austin, Texas for the year 2010. All right, so let's write down the equation. So we're going to plug in 2010 is going to be 60 years, right? Because 2010 minus 1950 is 60 years since, right? And plug in 60 for x. So we'll add that together. So 6.1261. That means y hat is equal to 10 to that power. Ten to the answer power. All right, so we get, in this case, we get 1,336,903 people. All right, there's our prediction. Okay, so number 42, the data for the global CO2 emissions from aviation for the years 2010 and 2019 is given. Because the data follows an exponential pattern, the emissions data was adjusted using a log transformation. So they took the log here. The third column of the data of the table gives the log of global CO2. Yep. The computer output for the regression log was given. Okay, for log. All right, so give the equation of the least squares regression line, define any variables used. All right, so the year, this is going to be year since 1910 is going to be X, right? So it's going to be X, or year since rather. So this is going to be X equals 0, X equals 1, 2, 3, 4, so on. And we're going to do log of Y. All right, so in this case, we got log of Y hat equals, and we got A, that's A, plus B, X. All right, where Y hat is the predicted global CO2 emissions from aviation, and X equals number of years since 2010. All right, so an exponential regression model was calculated as this, where X is the number of years since 2010 and Y is the global CO2 emissions from aviation. Calculate the log of 676.3153 and the log of 1.05. Okay, so they just want, it's a straightforward calculation. So part B, they just want us to calculate that. We got the log. All right, so we got 2.83, 0.15, and 0.0212. Okay. I'm just going to write down the two values. The next value was 0.0212. Okay, so I just wanted to calculate that. All right, so part C, how are the values of the parameters in the linear regression related to the values of the parameters in the original exponential regression model? Well, if you notice that when we took the log of this, we got 2.83, which was this number. When you took the log of 1.05, you got 0.021, which is this number right here. So you can see that those are related, right? And so we're going to say the constant term (2.83) is log of 676.3153. And the slope term, and the slope of 0.021 is the log of 1.05. Okay. So in other words, if you have the exponential equation, you can get the constant term and the slope by doing the log of each of those things. In other words, if you think about it, that makes sense because y hat equals ab to the x power. And we said earlier that you get log of y hat equals log of a plus log of b x. And so this is the slope. And so it makes sense that if you take the log of this, you get the slope. If you take the log of this, you get the y-intercept. That makes perfect sense, right? Based off what we said here. All right. So number 43. Why does applying a log transformation make exponential data appear linear? Let's explore this algebraically. Suppose an exponential regression model is given by that. So this is what we had talked about already. and I just wrote it down. So I'm not going to go through it again. Just go back earlier in the video. But this is equal to log of A plus log of B x. All right. Use the logarithm property. Oh, okay. So I guess I have to go through this whole process. Okay, so I guess we could do it again. So log of y hat equals log of a b to the x power. And if I use this property for this part, then I get log of y hat equals log of a plus log of b to the x power. And then use this property where you bring the power down to get it. All right, what type of expression do you now have? This is an expression y equals a plus bx. I'm just going to write like that, a plus bx, where b is the slope and a is the y-intercept. So you can kind of see that if you compare that. All right, so it's a line. All right, so number 43C, the expression, or the equation, the expression is now linear. All right, so number 44, the scatter plot and the table show the height and meters of a certain tree and the number of years since it was planted. The relationship is best modeled by an exponential function that looks exponential. Which of the following would result in a relationship that appears to be linear? All right, so if it's exponential, then that means we have to graph the log. If we transform it and do the log of y versus x, then that will appear to be linear. Okay, so that's what we want to do. Graphing x on the vertical, y on the horizontal, no. Graphing log x on the horizontal, log and y, no. Graphing x on the horizontal, log y on the vertical axis, yes, that's what we want. Okay, so let's look at 45. We're wrapping this up here. We've got a few more questions, about 6 more. Let's see, the population of lions in the wild has been decreasing according to a quadratic pattern. The scatter plot shows the relationship between the number of years since 1800 and the square root of the lion population. The equation for the least squares regression line is shown. 35.5059 minus 0.15094x. All right, so we got the square root. This is the square root of the lion population here. So the square root of y hat versus x. All right, so here, what does the model predict to be the lion population in 2015? Which means that x is equal to 215. All right, so we have the square root of y hat is equal to 35.5059 minus 0.5094 times 215. So we get the square root of y hat equals 35.5059 minus 0.15094 times 215. So we get 3.0538. All right, so now we need to square both sides, and that will help us solve for the y hat. So 9.326. And this is in thousands, right? So in thousands. Okay, so that's the lion population, 9.326 thousand lions. So the answer is on D. All right, so it's number 46. Now we're choosing the best model. The technology company Apple spends money each year on the research and development, R&D of its products. The scatter plot shows a relationship between the number of years since 2009 and the total amount spent on research and development in millions of dollars. All right, so it looks to be exponential or something like that, or at least power. So it's definitely nonlinear. Based on the scatter plot, do you think a linear regression model is appropriate? Well, definitely not, right? We can see that based off of the scatter plot. No. The curve pattern in the scatter plot indicates that a linear model would not be a good fit. Describe the relationship between the number of years and the total amounts. Okay, so we want to describe it. So, so again, remember, direction, strength, or strength, direction, form, and then unusual features, right? So it's pretty strong if we're talking about curved relationship. So there is a strong, positive, non-linear relationship between years since 2009 and total spent on R&D. There are no unusual points or features. Okay, so there's no outliers or anything that appears unusual on the graph. 47, the heights and weights of a random sample of 22 individuals are shown. The least squares regression line describing the relationship is given along with the R squared value and the residual plot. Okay, so we got the scatter plot, we got the residual plot here, and we got the computer output with the equation, standard deviation residuals, and R squared. Is a linear model appropriate for this data? Well, if you look at this looks to appear to be a linear trend. In addition, the residual plot, these seem to be randomly scattered. That's a good thing, that indicates. And not only that, the R squared is pretty decent, 0.8, so it's not bad at all. So I would say yes, it does appear. So we'll give several reasons, all right? So yes, scatter plot of data appears to show linear trend. The residual plot appears random, appears randomly scattered. About the zero line. And R squared value is close to 1. All right, so those are our three things. So in order to for a linear model to be appropriate, scatter plot needs to show linear trend. Residual plot needs to show randomness, and R squared value needs to be as close to 1 as possible. Okay, so those are the three things you want to discuss. Number 48, the correlation between X and Y with the relationship displayed in the scatter plot is 0.969, so that's R. Lewis is an AP Stat student who says that the best regression model for this data must be linear because the correlation is so close to 1. Do you agree? All right, well, I could come up with a regression model that looks like this, and that looks pretty good when I look at it. The residuals are, the points are pretty close to it. However, is that the best model? The answer is no, because just because you have a correlation of 1 or close to 1 doesn't mean that the data is linear. A better model here would be nonlinear, right? So you want to be careful to just not draw conclusions based off of just solely the R value, right? You want to look at the scatter plot, you want to look at the trend of the data. So no, a correlation close to plus or minus 1 doesn't mean that a linear model is a good fit. since the scatter plot indicates a clear nonlinear trend. All right, so just something to keep in mind. You just want to make sure the R or R squared value does not necessarily indicate, or the R value is not indicative of a linear relationship, right? That we can assume that's a linear relationship. It only gives us the strength of the linear relationship. However, there could be a form. It doesn't actually tell us anything about the form, which form to use, right? We have to look for the scatter plot for that. All right, so number 49, the students are often given a standardized math test at the beginning of the school year and again at the end to assess the growth of the students made. The scatter plot shows the average beginning of the year score and the average end of the year score for students in each grade level from kindergarten to 11th grade on a nationally administered test in a recent year. All right, so we got some data here. Based on the scatter plot, could a linear model be an appropriate fit for the data? Well, there seems to be a small curve to the data, right? So it may not, right? It may not be appropriate given that the scatter plot shows slightly curved data, a slightly curved pattern. Okay, so based off of that, it may or may not be, depending on, so it looks to be slightly curved. A least squares regression line is calculated and the residual plot is shown. Based on this new information, do you think the linear model is an appropriate fit? So they assumed that it was linear, and then they did a residual plot. Well, then when they did that, this is basically affirming what we said in part A. It does not appear to be a good model because it looked like it was slightly curved. Well, this is affirming that. There is a pattern to this residual plot. So that affirms what we said earlier. So the least squares regression line is not appropriate because the residual plot has a leftover, in this case we have a curve pattern, in the residuals. Okay, so we see a pattern there, so no, it can't be appropriate. Now, two other possible models for the data are shown. Which model is the best fit for the data? Give at least 2 reasons for your choice. Okay, so here we got something that looks to be more close to linear than it was. This seems to be less close to linear. This has a U pattern. This does have a pattern, although it's still less of a pattern than this guy. That's a clear U-shaped pattern, whereas this one, there's a little bit of oscillation here before you get to that the upside down U shape. So that seems better so far. The R squared value is greater than this one. So this appears to be the better model. It's not the best model, but it appears to be a much better model than what we see here, okay, based off what we see. So it can't be linear. It appears to be better than model 2. All right, so we're going to say model 1 is the better choice. For 1, its scatter plot appears to be more linear than that of model 2, than model 2. The residual plot shows less of a pattern than model 2's residual plot. And the R squared for model 1 is closest to 1. Okay, so those are the three different reasons for the choice. Scatter plots need just to be more linear. Residual plot shows less of a pattern. It's still a bit of pattern though, but it's less so. R squared is closest to 1. All right, so let's look at number 50. Number 50, it says the Cantril ladder is a 0 to 10 scale used to rate life satisfaction. The scatter plot shows a country's national average Cantril ladder score on the horizontal axis and the country's gross domestic product in dollars per capita on the vertical axis for 141 different countries. All right. Okay, so they're saying, okay, what effect does the Cantril ladder score have on the GDP, right? Maybe. So they graph the data. 3 possible models for the data are created. Each model's computer output and residual plot are shown. Which of the 3 models is best? So first off, they did score versus the GDP. So they assumed that it was a linear pattern. When they assumed that it was a linear pattern, they did the residual plot for that. And then for model B, they did the log of the GDP. And so by doing the log of GDP, they assumed, model B is assuming that it's an exponential graph, that they were saying it's exponential. Model C, they did the log of both of them, so then they assumed they were using a power model. All right, so which one is better? Determine the equation, so part A, which of the 3 models is best? So let's take a look at it in more detail. Let's look at model A. For model A, we have a low R squared value, 0.547, when compared to 0.614. This one's better. So model B has the best coefficient of determination of the 3 models. So that's something to keep in mind. If I look at the residuals, there appears to be a pattern here for the model A in the residuals. It does not appear to be random, in other words. There appears to be some kind of a pattern, some kind of weird spread out pattern like that. So it's not necessarily random. We're overshooting over here. If you notice that we're over, there's an underestimate there going on consistently. Model B appears to be more randomly scattered, so that's good. So that's better than Model A. Model C looks similar to Model A. There appears to be a lot of over or underestimation, and then a slight pattern, although less so than A. So B appears to be the most random. R squared is greatest here. I'm going to put most random. Yeah, so that's got to be the best model here. So be sure to define any variables used. Okay. Oh no, for part A. So we're going to say model B, since it has the most random scatter and residual plot, and the greatest R squared value, closest to 1. Okay, so that takes care of part A. Now look at part B. Determine the equation for your chosen model. Be sure to define any variables that you used. Now, since we used a log, we're using the log here. Okay, so we're going to say the log of y hat equals, this is my B, this is my A, equals 2.163 plus 0.348x. All right, so there's my model where y hat is predicted GDP per capita, x equals Cantril ladder score. All right, so it takes care of part B. And then for parts D, or yeah, for part C, so this is part B. Part C, use your chosen model to predict the gross domestic product. So let's do that, part C. Predict the gross domestic product per capita for a country with an average Cantril ladder score of 7.2. So X is 7.2. So log y hat equals 2.163 plus 0.348 times 7.2. All right, so let's do the math there. 4.6686, okay. All right, so then we're gonna, to find y hat, we gotta do 10 raised to the 4.6686 power. So we got 46,620, 46,000. 2.97. Okay, so yeah, we'll say what was it, 0.98 dollars per capita. All right, so that takes care of part C. Let me double check the number. All right. Okay, so then part D, the country with an average Cantril ladder score of 7.2 has a GDP per capita of 46,678. Using the prediction from part C, calculate and interpret the residual. Okay, so residual equals y minus y hat. So we got to take this number minus the number that we got. So we're going to do this number minus 48,678.68. And again, this is going to be a negative number, but the answer is going to be positive because I put this number second and it should be first, okay? So it's just going to be positive 2,055, okay? Per capita. And they want us to interpret it. So interpreting means that it's positive, so that means the actual GDP per capita is above or greater than or more than the amount predicted by the model, okay? So interpretation, the actual GDP per capita is $2,055.70 more than predicted by the model for Cantril score of 7.2. All right, and we finish off the last question. So 2 different regression models were used to describe the relationship between 2 variables x and y for a sample of 25 individuals. The equation of the least squares regression lines are given for models 1 and 2 in addition to the residual plot. Which model is more appropriate? Okay, so let's take a look at it. We got the equation and we got so let's look at the residual plot. There's a pattern here. That's not a good thing. There's less of a pattern here. It seems to be more random. So I'm going to give this to model 2. Model 2 because, let's see, which model? Yeah, this appears to have a more randomness. So it appears to be more linear because of the residual plot. So I'm going to say it's D, model 2, because X and L and Y have a linear relationship. Based off of the residual plot. All right, that's going to do it for the video, guys. I hope you found this chapter 3 review useful and informative, as usual. I'll see you in the next one.